Hello, this lecture is about light. Light is something we see every day. Um, it's not only used for vision, but also helps plants make food for us, and also makes pretty pictures like this one. So another term for light waves is electromagnetic waves, and electromagnetic waves are transverse waves. They have two independent polarizations. Um, Electromagnetic waves includes what we normally call light, which is what's visible or optical, but also includes infrared, ultraviolet, X-rays, gamma rays, microwaves, and radio waves. A polarizer can absorb one polarization but transmit the other one. The thing that's vibrating in electromagnetic waves are the electric and magnetic fields, rather than waves on a string, which is some displacement and velocity. Although some people think electric and magnetic fields might be related to some kind of motion in the vacuum. Okay, so this chart shows the different categories of electromagnetic waves called the electromagnetic spectrum, and they're classified here going from long wavelength down to short wavelength, starting with radio waves, which have wavelengths more than a meter, maybe even kilometers or larger. The next classification are microwaves, which are down in the centimeter or millimeter range for wavelengths. Then infrared, down in the tens of micrometers or micrometer range. Then visible, even less than a micrometer, hundreds of nanometers is another way of saying that. The ultraviolet waves, maybe in the tens of nanometers down to nanometers. Then X-rays are a fraction of a nanometer, and gamma rays are down around a picometer. Okay, and gamma rays are emitted from the nucleus of atoms, during some kind of radioactive decay. X-rays come from the motion of electrons in heavy atoms in particular. If an electron gets trapped in a heavy atom, it'll typically release an X-ray. Okay, and then the other interactions are more larger scale. Okay, here's a chart of frequency. So remember, frequency multiplied by wavelength gives you the wave speed. So all these waves have the same speed, the speed of light. So if you're going in order of decreasing wavelength, that's the same as increasing frequency. So radio waves are considered low frequency for light, even though they're like kilohertz or megahertz range. Then microwaves, would be up around 10 to the 10th cycles per second. Visible light, up around 10 to the 14th cycles per second. And then you get up around these gamma rays around 10 to the 20th cycles per second. So just incredibly rapid vibrations for some of these waves. I'll just say you can't really measure this directly. What you can more or less measure directly are the wavelengths, and then we can infer the frequency once we know the wavelength. This last graphic here is the temperature that an object would have to be to radiate at a certain frequency or wavelength. So you all know the expression red hot. If something gets hot, it glows red. So that happens in the range of several hundred degrees Kelvin. And even just a warm body, will glow in the infrared range. The sun is around 6,000 degrees Kelvin. and that glows. Green light is the peak. And of course, if something's white hot, it's even hotter than that. Okay, so white hot would be maybe over 10,000 degrees Kelvin. Okay. So the intensity or brightness of light is the power per unit area perpendicular to the direction of propagation. And that area, the fact that it has to be perpendicular is important because you can be on the North Pole, but if you point your solar panel at the sun, you're essentially getting the same amount of light as if you're on the equator. Okay, so the reason that the poles don't heat up as much as the equator, it's not because there's less light coming from the sun, but it's because the surface that that light is hitting is at an angle. So if the light hits perpendicular, you get the full power, the full brightness per unit area, the power per unit area. But if the surface is tilted, like the poles are almost, the surface almost parallel to the path the light is propagating. So the light gets spread out over a bigger area, and that's why you get less heating. If a pulse of light is emitted from a source, it'll move outward in kind of a spherical shell propagating outward. And for a given amount of area on that sphere, the further it propagates, the bigger the sphere, and therefore the brightness is reduced proportional to the area. So the intensity, the power per unit area, must drop off inversely proportional to area, which is inversely proportional to the square of the distance. So that's called an inverse square law. So as an example, I think Jupiter is about 5 times the distance from the sun and from the Earth, the distance away from the sun compared to the Earth. So it only gets about 1/25 of the sunlight that the Earth gets. Okay, if we look at the solar spectrum, it peaks in the visible range, something close to green light. Drops off rapidly at higher energy or shorter wavelength. And then it has this long tail for longer wavelengths. Okay, the yellow here is what reaches the Earth's atmosphere, and the red is what reaches down to the surface of the Earth. Okay, so of course we get lots of visible light. We get not too much ultraviolet, which is good because that causes sunburn. You can see that's absorbed by ozone in the atmosphere. And the infrared, some of it gets absorbed by water vapor in the atmosphere, and some of it gets absorbed by carbon dioxide. And the Earth actually, because it's warm, it actually emits infrared radiation as well. And the whole thing about global warming that you've probably heard about is because with increasing carbon dioxide, the atmosphere is absorbing more and more of that infrared radiation, so it doesn't escape out into space. Okay, so different colors of light just represent different frequencies. So red light has wavelength around 700 nanometers, frequency 428 terahertz. So that's tera is 10 to the 12th. So 4 times 10 to the 14th hertz. And light comes in packets that are called photons, and these are the energies of each photon. So anyway, the range is really fairly small range, from 470 nanometers to 700 nanometers. Okay, I mentioned that light is transverse wave, so it has 2 different polarizations. And there's actually some crystals which have different light speed for different polarizations. And the path of the light bends when the speed changes. So looking through the crystal, you actually see double. You see 2 images of whatever's under the crystal. And One crystal in particular, which is a type of calcite, was used by the Vikings to locate the position of the sun in the sky, even through fog. And the way that was done was that the light that's reflected from the sky at 90 degrees is polarized. So you can figure out what direction is 90 degrees from where the sun is. Also, polarization of light is used for other purposes, like sunglasses. Polarized sunglasses reduce glare because reflected light is strongly polarized parallel to the reflecting surface. So if you block that, then you reduce the glare. Also, 3D movies, you put on those little glasses. They have different polarizers for each eye, and that allows each eye to see a different picture on the screen. Your eyes contain 3 different pigments. They're sensitive to different colors, and those colors are called the primary colors, red, green, and blue. They're actually kind of overlapping. I'll show you a picture in a minute. But you interpret whatever color you interpret with your eyes is based on the combination of these response of these 3 pigments. So these are the actual sensitivities for the red, green, and blue pigments in your eye. Okay. And the different cones that detect color, they also kind of respond at different rates. So you can actually take some kind of pattern of black and white, and if you flash the black and white appropriately, you can make it appear colored. There's a thing called Benham's wheel or Benham's disc, which you can look up on the internet, although I didn't have much success watching it on video. You really have to make one and watch it live. Okay, light bulbs provide us with light. And remember that intensity or brightness is the power divided by the area, so watts per square meter. So much of the radiation from a light bulb is actually infrared or heat. You can tell that if you hold your hand near a light bulb. You'll feel it's typically kind of warm. So the actual visible power in the light is measured in what's called lumens, and 1 watt of visible light is about 683 lumens. Okay, and that's approximate because it does depend on whether it's red or blue, what the distribution of colors is. Okay, so the efficacy of a light bulb is the lumens per watt, and that's what's plotted in this graph. You've got the old incandescent light bulbs have very low efficacy. Mostly they just give off heat. And then you can see increasing efficacy. Compact fluorescents have been popular until recently. And of course, office buildings often have these big linear fluorescent bulbs. More recently, LED bulbs have moved into the mainstream as their costs come down. And for the price, they're the best way to generate light currently in your home. And they have efficacy, somewhere 80 to 100 on the upper end here. Okay, so that's efficacy, which is lumens per watt. But the efficiency, remember, is the useful energy output divided by the total energy input. So if you're getting 100 lumens per watt, and 1 watt, remember, is 683 lumens, that's still only about 15% efficiency. So don't confuse efficiency with efficacy. Okay, those are 2 different things. Okay. All right, so when light encounters a surface, two things can happen. It can reflect, in which case the direction parallel to the surface, basically the speed doesn't change, but it reverses the speed perpendicular to the surface. Okay, that's reflection. And the second thing it can do, it can be partially transmitted, but the direction changes. Okay, and that's called refraction. So in different materials, the light will travel at different speeds, always slower than the speed in vacuum. And the ratio of the light speed in vacuum to the speed in the material is called the index of refraction, or refractive index. Okay, and here's just a few examples. Glass, air. Typically things are between 1 and 2 for most materials. Diamond is exceptional, has a pretty high refractive index, although that's not the reason that they sparkle. The reason you get the different colors is because that refractive index is slightly different for different colors, for different frequencies. So the different frequencies or different colors bend just a little bit different directions in the diamond. So depending what angle you look at it, you see a different color. Okay, when light crosses a boundary where the speed changes, what happens is the path of the light gets bent. So here I've got a picture here. Imagine these yellow lines are wave crests coming in from left to right. When they encounter the slower material, the waves slow down, and notice they just start to lag behind. And the result is that the wave crests are now lined up in a different direction. And of course, the wave propagates perpendicular to the wave crest. So actually, the direction of the wave has changed to this arrow. So if the speed is decreased, the wave bends toward the perpendicular. If this were a faster medium than the one outside, then it would bend the opposite way. It would bend away from perpendicular. Okay, so waves propagating from one medium to another. The reason with the slower speed, okay, if you look at the picture, you can see where there's a slower speed, you get a smaller wavelength, because just the sort of bending of these wave crests makes them end up closer together. But the frequency can't change. If you look on the boundary here, you have to have the same frequency on both sides of the boundary because the wave crest is continuous. So the frequency doesn't change. Okay, so you have to have the same frequency and a shorter wavelength, and of course a slower wave speed. Okay, so in many materials, the speed of light varies with color. Prism is an example of that. And that means that the light of different colors actually will travel different directions. Okay, so you can actually separate the colors. That's how water droplets work. The light goes into the droplet, gets refracted, so the different colors change direction slightly different amounts. Then it actually gets reflected off the back of the drop and then comes back out. So here's a nice picture of a double rainbow. What actually is happening here is what I described initially. The light goes in up here, the light would go in the top of the drop, reflect off the back, and then come out the bottom of the drop. That's what's happening here. When you get to the second rainbow, the light's actually going in the bottom of the drop and then reflecting twice and coming back down. Okay, and then in between, there's actually no light getting reflected from the raindrop. That's why it's dark in between. Okay, there's a nice lecture you can look up when you get a chance. Okay, since waves normally propagate in straight lines, it's possible to form images. So if you have light from some object, you just shine it through a hole, then put a screen on the other side, and you'll actually see a picture of that object. Okay, that's called a real image. And you can make the hole bigger if you put a lens there, so that the light still gets bent and focused back here and makes an image, but you have a larger opening so you can get more light. And with the lens, all the light coming in a single direction will focus at a certain point on what's called the focal plane. Okay. And you can also have a concave lens, which causes the light to diverge instead of focus. But if you take that diverging light and follow it backwards, it's as if it focused behind the lens, and you actually still get an image, but it's called a virtual image because you wouldn't see anything if you put a screen there, but if you just look through the lens, there's an illusion that there's an image there. So that's called a virtual image. Okay, an interesting property of light is, or any wave actually, is the interference and diffraction, which occurs when you have multiple components of the wave combining into a single wave. So an example of that is if you take light and shine it through a slit, and then look at a screen far away. If the light from the two slits, well, in general, it has different path length. You know, the light goes a different distance. Has to go, you know, to get up to this point, it has to go farther from the bottom slit than from the top slit. If that difference in length is a multiple of the wavelength, then you get a bright spot. Because the waves that were lined up coming in, the peaks will still be lined up over here. If this extra length is a half wavelength or some odd multiple of half wavelength, then the waves are going to cancel over here because you'll get a peak from one side and a trough from the other side. Okay, so when you shine light through two slits, you get this pattern of bright and dark, and that's called the interference pattern. Okay, and you can actually, you know, calculate, you know, what the spacing is going to be. So there's some similar triangles here. So this extra path length divided by the spacing, d, is equal to the distance along the screen here, s, divided by the length. Okay, so this is just sort of comparing that interference pattern for water waves here in the box and the pattern you get for light waves here. And you know, the idea is the places where the waves add together, you get a bright spot. Places where the waves cancel, you get a dark spot. Okay, and it turns out you still get this kind of interference even if you just have one opening. You can think of it as two slits that are just side by side with no separation is one way to look at it. And in that case, when the light comes through the slit here, it still makes an interference pattern. And we have a special name here for the distance between the central peak and the first minimum. We call that the blur. Okay, because as the slit gets smaller and smaller, that blur gets bigger and bigger. All right, notice the formula is inversely proportional to A, which is the width of the slit. Okay, and this is important for things like telescopes, because if your telescope has a fairly small opening, that means that your image is going to be blurred. So that's why astronomers always want great big telescopes. Partly they get more light from it, but also they get a sharper image if they have a bigger telescope. They get smaller blur. Okay, and you can actually observe this diffraction. An easy way to do it is take two pencils, hold them together, touching, and then just slightly separate them. And when you do that, you'll actually see this pattern of dark lines in between the pencils. And I actually have a picture of that here. You can see there's these dark lines, at least two of them, between the pencils. So that's diffraction. Okay, so if you're looking through an opening, let's say you're an astronomer, you look through an opening at some distant object. If the two objects are too close together, like less than the blur, they'll just look like one object, so you won't be able to distinguish them. All right, so that blur is the ratio between, well, let's look at it this way. The ratio between the blur and the distance is the same as the ratio between the wavelength and the aperture. Okay, so the formula for the blur is the wavelength times the distance divided by the aperture. Okay, so that tells you how far apart two objects need to be for you to be able to tell them apart. Okay, thank you for watching.